we're waiting for the Facebook Live. Hold on. 1.5 fans are waiting. Right. But the millions of people will watch your video. That's right. Okay. All right. Okay. We are live now on Facebook. Okay. Go ahead, John. You're on.
Now, David, you know how to say lights, camera, action.
You're on. You're on.
Okay, my name is John Eichler. I'm in Little Rock, Arkansas, where it's 95 degrees today. And I'd like to give this little presentation for a new mechanism for matter increase within the Earth. Now, before I get into the whole presentation, what I would like to do is to give a little idea of what my motivation was in getting into this whole area to begin with. My original goal was to get into physics back in my undergraduate days. But along the way, like many people, that was a little bit waylaid and a little crooked path. So I'd like to go back to that time period and talk about two paths to an expanding universe. I mean, an expanding Earth, I'm sorry. One path is the empirical approach. This is where fellows like James Maxwell come in, because he's out there digging the rocks, at least he's supposed to be, he's a geologist, and he uses, along with other empirical approach people, inductive reasoning, going from various instances that he has investigated as far as rocks and everything to a general conclusion like the Earth is expanding. The other approach is more of a theoretical approach where you use deductive reasoning. In other words, you start from a hypothesis and then you home into a specific instance. This is the path that I took because I was, at the time, planning on becoming a theoretical physicist. Now, before we get into the whole speech, I want to mention what the Doppler effect is. And most of you probably know this already. But if you have a stationary source putting out periodic wave motion, you hear it the same or see it the same in all directions. If you have the source which is moving, it in effect compresses some of the waves on the front end and expands them on the rear end as shown. Now, back in those days, I wanted to go, and I'm going to turn my volume down a little bit so it doesn't, there's a little bit of a time delay. But anyway, I was looking at stars out in the universe and saw that there was energy being given off, which, as most of you are familiar with, you end up with a red shift of the light coming toward Earth. From the standpoint of a steady state universe, to me, it seemed that there must be some mechanism somewhere where this energy which was given off by stars would be reclaimed or recycled. Otherwise, you're going to end up with a one-way street scenario, and the universe is going to run down, which I think an infinite universe should not run down. In the 1957-58 time period, as I said, I thought there'd be an infinite universe with this energy given off by stars. There has to be a reverse process somewhere. That got me on the whole path. And once again, as I said, they undergo a red shift from Planck's law. If you end up by losing energy, you get longer and longer wavelength. The longer wavelengths can penetrate further into objects. This led me to the conclusion that the one good place for energy to be absorbed might be planets like Earth. Now, I've changed it, of course, over the years. I've changed my mind on that, but this is where I was back in that time period. but I really didn't know enough about the interior of the Earth. So I headed to the nearest technical bookstore. I got this book. I don't know whether James might be familiar with it there, Internal Constitution of the Earth, vintage 1951 or thereabouts. And what I learned from the book was one, the source of the Earth's heat is an unanswered question. And that fit right in, by the way, with my idea of absorbing the energy as it got longer and longer into the Earth. And two, this diagram from Wegener about his continental drift, the shape of Pangaea, which looked oval to me. And in contemplating this drawing a little bit more, I thought, gee, that looks like it might have been on a smaller Earth. So in 1957, when Sputnik went up, and then in 1958, when they finally got a Vanguard rocket up, the Vanguard once again had a very small satellite, 6, 8 inches in diameter thing. Well, anyway, when that got up and they had some time to investigate the motion of the satellite, they discovered that the Earth seemed to be expanding a little bit or bulging out in the South Pacific Ocean. And this fit right in with what I was thinking at the time. If something heats up, it's supposed to expand. And consequently, you have, as this drawing from Harry Hess, who was one of the pioneers from the standpoint of the oceanic floor mapping, shows, under the ocean you have basalt, which is relatively thin, maybe 5 kilometers, and under the continents you have 30, 35, 40 kilometer depths. So to me, believing at the time that the Earth was expanding, and by the way, most of the people I talked to at that time, even though I worked at a research institute, most of the people I talked to thought I was loonier than a lunatic. But to me, this made perfect sense. So going into the 1960s, I was convinced the Earth had undergone expansion. So in my view, plate tectonics was completely taking the wrong path. I had never gone along with plate tectonics, although I've done some reading about it. Well, now I had this idea, and I thought for a 15-year period that I was the only person. Back then, we did not have the internet. It was very, very difficult to try to gain any type of information about what's going on. I thought that I was probably the only person who held this weird idea that the Earth was expanding. Well, it turned out about 15 years later, I bought a book that was written by a man named Walter Sullivan. He was a science writer for the New York Times, the head of that. And it mentioned Warren Carey from Tasmania. And in the book, he talked about the skydiver from Tasmania. Apparently, Carey, during the Second World War, did a lot of skydiving and this type of thing. So I wrote a letter to Warren Carey, and I asked him about a 1955 conference he had. He came back to me, a package came back about 2 inches thick, and he explained that they had done 2 copies of the proceedings for that conference, and he's had hundreds of requests for them. However, because of my interest, he had a secretary actually copy one of those interests. In fact, when he came out with his landmark book, An Expanding Earth, in 1976, he actually mentioned my name and said that I was interested in the red shift, and I thought that that had something to do with it. Well, anyway, I got into the field of computers. I was working for a research institute, got off in the field of computers. I was programming shockwave motion for nuclear reactor blast shields for a number of years, and consequently, like things occur, it was just a little bit too much for me. I couldn't keep up with all this. But then let's hop again 30 years into the future, and I'm in Arkansas, and I started going back to school down at the University of Arkansas, taking some classes. I started on a master's program in 2006. In 2007, I was thinking about writing a book, and so I ran across, once I came up above the water and looked around at Expansion Tectonics again, I ran across James Maxwell's name. I talked to James. We made lots of very interesting conversations about the dynamics of the Earth. Once again, James is coming to it from a geologist standpoint. I was coming at it from a theoretical standpoint. I had no idea of what anything in geology was like. But I wanted to write a book on not only the expanding Earth, but several other topics. And I wanted to write a draft, on the book, I was calling it An Infinite Universe. So I grabbed a couple of chapters of the book and made it into my master's thesis. Both James and my professor that gave me this year-long independent study to do said that I had talked about everybody else, but I should interject some of my own ideas about expansion tectonics into the subject that I was writing about. Well, I took this opportunity to start doing a little research, and I came up with a suggested new mechanism for mass gain of Earth. Now, Carey had in all of it, I think Carey wrote 3 or 4 books, but in each of the books that he wrote about, he mentioned several possible ways that were causing the universe to expand. One of them, and he rejected all of these. One of them was a pulsating Earth, does not satisfy the exponential expansion observed. Meteors or asteroids striking the Earth, once again, that doesn't explain the ocean floor. The original Earth having a massive core or a massive high density core, but since the Earth has expanded like 50 times the volume, that's not too, because otherwise you'd end up with this tremendous density higher than anything else that we see around. Gravitation changed over time, but that was not able to explain some of the facts he had. And the increasing of the mass of the Earth, let's see, on my slide, I can't quite see where it is, but nothing like that has ever, the increased mass of the Earth has not been known. Now, I want to say all matter that around us, or at least most of it, except if you're around a high particle physics, is composed of protons, electrons, and neutrons. Protons and electrons are stable. The free neutron actually decays and has a half-life a little bit over 14 minutes, decaying into a proton, electron, antineutrino. So you must have, and this is something that became obvious to me, you must have protons to make new matter. Now, somebody has suggested that maybe pair production, that's when a photon comes close to a nucleus of a larger atom, it breaks down into an electron and positron, but you need very energetic photons to do that, and positrons are not protons, so you can't do that. In fact, with quantum electrodynamics, it shows that this photon-electron interactions, you end up with positrons all over the place, but most of the positrons are absorbed or combined quickly with electrons, and you end up with a photon again. Now, if the Earth is gaining mass, the mass must be coming from somewhere. The process must be via a mechanism which does not violate the known laws of physics or results based on empirical laboratory experimentation. Anyone can think up very elaborate esoteric theories, and the 5 that I mentioned earlier I regard as very, very esoteric. But I am a firm believer in physics and the fact that you want any kind of explanation to go along with the laws of physics. But here, as I say, as is shown, I said, or results based on empirical laboratory experimentation. You'll see why I put that in there, because if you have experimentation in the laboratory which shows something, then you can incorporate that. Any newly proposed law of physics must be able to be falsified by experiment or logical reasoning. If a hypothesis has no means by where it may be proved false, then it's called pseudoscience. And this is a definition from Karl Popper, who was a philosopher of science. Now, the summary of my new proposed mass gain mechanism is as follows. First, because the electrical and this is an overview, because the electrical characteristics of Earth allow charged particles, both protons and electrons, to be conducted in Earth's interior. In fact, when I got this idea about proton conduction, I had never heard of it before, because once again, I was in the field of computers. And so I did some research down at the university and found, yes, proton conduction is relatively old. Cold fusion takes place, and I'll get into that in a few minutes, takes place making new mass and raising the Earth's heat. You get transmutation of elements. This is one of the very interesting things about cold fusion. And once again, I'll mention this a little bit later, where not only do you get the fusion of the deuterium to make helium, but also you end up with all kinds of new elements coming up. And as a result, the Earth gains mass as time progresses. Now, the question comes up, where do you get all these protons from? Well, from solar particles, you end up with sufficient mass coming in to give you almost a infinite amount of material to grow from. Something that's very interesting here is because the Earth has a very large magnetic field footprint, you end up with a larger cross-sectional area, effectively, than you would from just the physical Earth itself. And another very interesting phenomena is the electrical characteristics. You actually have in the whole atmosphere and I get my pointer over here, you have between the ionosphere and the Earth, you have anywhere between like 250 to 400,000 volt potential. We're living in the middle of a big capacitor. And whether you know it or not, we've got electrons and protons going back and forth in this field. Once in a while, the capacitor will break down and you'll end up with a lightning discharge, but you end up with this electrical circuit for the entire Earth. Now, size matters. For those of you that aren't familiar, I thought I'd throw this slide up there. 1 millimeter, and the 1 millimeter is the small division, of course, over on the ruler there. That's a thousandth of a meter. 1 millimeter equals 100 microns. A micron is really a millionth of a meter long, pretty small. Now, a nanometer is a thousandth of a micron, which means it's a billionth of a meter long, very small. When we get in nanometers, light, for example, the wavelength of light is visual light is like 400 to 700 nanometers. Then you get down to the angstrom. Now, 1 nanometer, billionth of a meter, contains 10 angstroms. An angstrom is a tenth of a nanometer. And then you get down to femtometer. Now, a femtometer, 1 nanometer is equal to 1,000,000 femtometers. In other words, that is a billion millionths, or a billion times a million femtometers is 1 meter. So it's a pretty small number. Okay, to give you a relative idea, diameter of a water molecule, and by the way, water molecules are one of the smallest molecules there is about 2.9 angstroms. So it's way less, a quarter of the size of 1 nanometer. The diameter of a hydrogen atom is about 1 angstrom, and a proton, in comparison, is 1.75 femtometers. That is about 1/60,000th the diameter of a hydrogen atom. Now, one of the things that got me off on this was that if you have hydrogen, hydrogen will penetrate to some extent, but hydrogen atoms are pretty doggone big. When you get down to protons, protons are so small they can go through anything. They're so tiny, which gives them a certain amount of mobility. So I got off on proton conduction, and the first one is the Grotthuss mechanism. And you can see in the first diagram on the left, water, it turns out, has, even though you have H2O, water will pick up spare protons. And the binding of those protons are maybe 1/20th of what a regular covalent electron would be. And the water molecules are changing these protons all over the place. So what happens is you get a bonding of a proton to 2 hydrogen to two water molecules, and then you end up with a breaking off of one and going to the second one, which transfers the charge. And of course, if you have three protons, extra proton in a water molecule, it becomes positively charged. So you can see the charge moving, and it moves all the way across. So it starts out on the left and ends up on the right. That's one mechanism that protons are conducted in water. And you end up with these things like the Zundel molecule, and the Zundel molecule is H5O2, and you can see there that right in the center, it's only like two, if I can read it here, is 2.4 angstroms across, and you end up with these molecules, and these molecules will transfer protons. Well, it turns out the proton conductors are all around us. Water and ice are both excellent proton conductors. So are now James is going to get me for saying this, but perovskite, again, the perovskite crystal structure. Now it turns out that that crystal structure makes up most of Earth's mantle, and it happens to be a very excellent conductor of protons. Now I'm going to talk a little bit about cold fusion, and this is also known as low energy nuclear reactions. Okay, now here's an example of hot fusion versus cold. Over on the left-hand side, you see this guy inside this huge device that is supposed to keep protons spinning around, getting energized, and creating energy. And below that, you see the dollar. You're talking about billions of dollars for these type of reactors. On the other hand, in cold fusion, you have something which is very simple. It's a beaker. You have a regular electrolysis setup, an anode and cathode. You have an electrolytic solution within that. In cold fusion, most of the experiments are done with the anode, nickel, and the cathode sometimes can be nickel, but usually it's palladium. And you just do electrolysis. Well, what happens is that the water, the solution in there is heavy water, is deuterium water rather than regular hydrogen water. Deuterium is a hydrogen atom, and it has a neutron plus the proton in the nucleus. Well, what happens is then you do electrolysis, and on the cathode, after you end up with enough deuteron nuclei entering in and embedding themselves in the palladium electrode, cathode, after you have to get it really saturated, and then you end up with this cold fusion phenomena. Well, what's the difference between the cold fusion and hot fusion? Well, in hot fusion, you take two deuterium nuclei, you bring them together at a high rate of speed and energy, and once you end up with this reaction, you get gamma rays off, neutrons, you get helium-3, which is a very rare type of helium. It's like 200 parts out of a million helium-4 atoms. And you get tritium, and proton and neutron sometimes. But the tritium is a form of hydrogen. It's an isotope of hydrogen. It has one proton and it has two neutrons. And it happens to be radioactive. And the half-life of it is 12 and a half years, which is we'll get to in a little while. Now, on the other hand, cold fusion brings together two deuterons, which are the nuclei of the deuterium, and it fuses them together, no byproducts, and you end up with heat energy coming out. Cold fusion should not happen. The reason why is you have a Coulomb barrier that prevents the charges coming together, just like the repulsion with magnets. Try and push two magnets together, they resist each other. That's why with hot fusion, you need to get the protons going at the nuclei going at a high rate of speed so they can get over the Coulomb barrier. And there's been different considerations, and some people think that the protons will tunnel through a quantum mechanic effect, but they really don't know yet. There's no current theory in physics that can explain cold fusion. There's a lot of people that have tried. I mean, there's actually several hundred theories out there, but none of them have been settled upon yet. And cold fusion, by the way, literally turns current physics upside down. Now, to give you an idea of what a cold fusion experiment is like, uh, the object, of course, is to see if there's excess heat produced by the reaction. And this is a sample container. You can use a beaker, but generally, if you have heat and things and you want to analyze the byproducts coming out, so what they do is this is one that a Japanese gentleman put together who had done research on this. He uses a palladium mesh, no, yeah, a palladium electrode, and he has a platinum plated electrode. He has thermocouples in there. They have the solution, and then up above, see where it says the black catalyzer, platinum black catalyzer. Well, what they do is, like any electrolysis, if you're doing it, you get hydrogen and oxygen out. In this case, you get deuterium and oxygen out. It might explode if you put some catalyzer up there. What it will do, it will combine them back together into the liquid again. So you put this closed container, which is essentially the little reactor thing, in a water bath. And then you measure the water very carefully, and that's how you can tell whether you're getting excess energy. You know how much energy you're putting in from the standpoint of electrolysis. This way you know how much, if you're getting more energy out than you're putting in. Now, first, when they did this, it's very hard to replicate this, although now it's getting easier. Some people have even gone and taken a palladium liquid, palladium and oxygen liquid, and put deuterium, heavy water in. And what it does, it actually plates on your cathode a combination of palladium and deuterium. If you don't do this and you want to get it saturated, sometimes you have to go for weeks with the experiment going before you end up with getting enough deuterium into the palladium to cause a reaction. This other way, in a day or so, you can actually build it up enough. And there's active research going on right now, both experimental and theoretical. This is a graph showing the regions of the cold fusion reaction. If you get up by the Rossi region, you've got a nice sustainable heat coming off. Above where it says runaway region, you actually, and many people have experienced this. In fact, that one container I showed you, the fellow that did the thing started the reaction. It was getting hot. He was in water. He went in the morning, and the water had almost all boiled away. He put more water in there. He stopped the electrical current for the electrolysis, and he went through several days where it was just giving off heat. And they put liters and liters of water in, and the stuff would all be boiled off. So once in a while, you can get that type of a reaction. Now, I mentioned transmutations a little bit earlier. These are a couple of graphs gotten from a couple of experimentation labs, and where they end up by getting the original high-grade pure palladium electrodes. Afterwards, when they take into the lab, they end up with all kinds of various elements that were produced. It's almost like alchemy. And in fact, in one case that I read about, the nickel actually went and it converted 40% of the nickel to other elements. So it has a lot of purposes there. And there, I think in the back of my mind, gee, if you're having this going on the inside of the Earth, maybe some of the elements that are formed are actually formed in the Earth right under our feet. Okay, now is there any evidence of fusion happening on Earth? Well, of course, I will say my obvious answer is yes. The Earth is expanding. But that's very subjective on my part. So is there any other evidence? Well, there are two things. One, there are two stable isotopes of helium, helium-3 and helium-4. Helium-3 is very rare on Earth, but is found in much higher abundance, 10 to over 100 times and more higher in gases emanating from the Earth. And the gases that they find it in are two places. One in volcano or crater lakes, old volcanoes, where you end up with not much water coming in, and the water at the bottom being very stable for thousands of years. And they go down there and they pick it up and they find helium 3 in that type of water. They also find it, by the way, in the bottom of the ocean in different places. And the other thing you want to look for is tritium, which is the isotope of hydrogen, which once again is found in these volcano and deep lake gases. By the way, just out of interest, they find these gases not so much from surface volcanoes, but really the deep ones go all the way down to supposedly the core mantle boundary. So the assumption is that they have come in through the mantle and got into the water that way. So summarizing cold fusion, it definitely seems the cold fusion reaction is a real one. There's too many scientists worldwide, and if you look up, there's actually thousands of articles on cold fusion and dozens of books on cold fusion. It's a hard thing to do, but those people that have stuck with it are closing in once again on this cold fusion effect. And you ask somebody that has actually seen the cold fusion happen with the excess heat, they're convinced. I mean, nothing can convince them. The theory behind it is not known, although there are multiple theories out there that have been proposed. Research continues actually in many countries around the world. Much of it is government sponsored. In the United States, I don't know how much is right now, but the Navy has spent millions of dollars in researching this, and it's a really cheap way of energy. And slowly, mainstream skepticism is beginning to be overcome. But there's an effect there. I'm actually, from all this reading I've done, I'm absolutely convinced of it. There's some really brilliant people working on that problem. Now, here's a couple scientists. Okay. Now, I'd like to bring up a new speculative hypothesis that I came up with. And this, I even haven't talked to James about this yet. So, James, you might be really interested in this because I use your data. What we seem to know is from the work that James has done, and this is out of his book, that the Earth has started to experience expansion back around the 1.5 billion years ago. And all of a sudden, the doggone thing has gone exponential on us. Well, the Earth's radius has increased by a factor of about 3.75 over the last billion and a half years. And remember, the Earth's estimated to be about 4.5 billion years old. The area has increased by a factor of 14. The volume has increased by a factor of 52. That's why if you if you hold the view that the Earth was very dense to begin with, it would have to have a density fantastic, more than any place else that we've imagined in the solar system. However, factoring the rate of change of the radius is not linear or by x squared or by x cubed, but rather is exponential. Exponential growth. Of course, that growth rate is proportional to the function's current value. Examples, biology, of course, if you have a lot of more microorganisms and food, they will just grow exponentially. Nuclear chain reactions are exponential growth. Compound interest, you can think of numerous examples that are examples of exponential growth. But why exponential? I started pondering this. Why all of a sudden do we end up with this exponential? Well, once again, if it was an area phenomena causing the growth, we would expect it to pretty much follow x squared, because pi x squared, of course, is the surface, or the diameter squared, whatever it is a square function. Volume, of course, follows as 4/3 pi r cubed. But here we have exponential. Now here's a chart, and you can see way down at the bottom, this bottom green line is x squared. Then you end up with x cubed. But all of a sudden you get this exponential. The reason why you don't see any curve down there is because, look, 10 e to the 10th power is 22,000. It's incredibly high. So let's take a little bit closer look at James's curve. Now, James only took that particular curve out to 2.5 billion years, but actually we know the Earth is about 4 billion years old. So if you go out here to the 4.5 billion years and look at it, we see that it's almost flat. In fact, if you talk to James, he'll tell you that it probably has increased in radius microns for the first 3 billion years. And then all of a sudden it goes exponential. There's the exponential curve I showed on the other slide. So we end up with two major questions. First, why no growth for 3 billion years? And second, why exponential growth for the last 1.5 billion? So what I did is I pulled out my geological time chart, which I had made, and I sent this over to James and asked him if that would be a good chart to have. And he, of course, sent it back to me, and I'm going to take this chart, I'm going to go 90 degrees clockwise on it. And this is the chart he sent back to me. He likes all of these fancy colored areas, but you can see that you end up by over here having the one-celled organisms, small continental seas, and then you have the vast continental seas. This is before the oceans opened up. Then over here, about 250 million years ago, you ended up with the oceans opening up, reptiles, age of mammals. But over way at this other side, you end up with, well, coming here from about 25 billion years to 45 billion. Here you're talking about 3 billion years, more or less, where you had no growth at all. So what I did is I arbitrarily chopped this at the 1.5 billion year mark. So we have 3 billion years on one side and 1.5 billion on the other. And I applied it to this graph. And what I found was these small continental seas, and once again, this is the approximate beginning of the expansion. These continental seas were when you end up by getting very little expansion. Then you got into the part where you had the vast continental seas covering great portions of the continents. And what happened? You got a little more, and then you got the Pangea breakup and the modern oceans, and the thing went up like this. Ha, I thought. Question: is the growth of the Earth proportional to the amount of ocean surface water on the Earth? And furthermore, is there a positive feedback loop governing the expansion of the Earth? Now, this is kind of an interesting concept because all of a sudden, if it is proportional to the amount of surface water, then as more and more surface water comes to the forefront, you're going to get a larger and larger expansion. Very interesting. So my hypothesis is this, my new hypothesis. One, given the electrical characteristics of the Earth, and we know that we have conduction of both protons and electrons everywhere, and the Earth really is a very conductive body. And the propensity of water on the Earth to allow the mechanism of proton conduction, my hypothesis is that that exactly is what happens. In other words, the rate of growth of Earth is proportional to the amount of surface and near surface water on the Earth. That would explain the 3 billion years of lackadaisical performance, and then all of a sudden the vast exponential expansion. I'd like to give a little bit of a philosophical overview. You know, we live on almost like a flat Earth. It's hard to go up, and it's very, very hard to go down. Looking up toward the heavens, after Hubble discovered Hubble's law, which relates the distance to the red shift, Hubble never believed that the Doppler effect was the cause of the red shift. He always felt that light, as it went through space, was a tired light type thing, and some physical mechanism was draining the light of energy and causing its wavelength to increase. Actually, Hubble spent the remainder of his life looking for a scientific way to prove that the redshift was due to another mechanism, thereby making this what he called sensible and a non-expanding universe in which we live. The rest of the scientific community nevertheless developed the paradigm of the Big Bang, and that has shaped. Hubble, I know, is called the person that showed the universe was expanding, but Hubble never believed it for his whole life. And this is not the only thing about cosmology, and you don't want to get me started on cosmology, but they're in kind of a paradigm rut too and can't seem to get out of it. Now that's looking up. Now let's go and look down. The surface of the Earth is like an eggshell. The thickness, and I'm going to give you a couple figures here, the thickness as a percentage of radius. On an eggshell is 1.8% of the radius of the eggshell. That's a standard egg. The continental crust of the Earth, and I'm talking about the continents now, are 0.6%. And the Kola super deep borehole, which is the furthest that we've ever gone in, is 12.3 kilometers down, is like 0.2% of the radius. That's 1/500th of the way into the Earth. And they had to stop because they were running into high temperatures and all kinds of stuff was happening. We can't get down there. It's more of a challenge to get down into the Earth than it is to go to outer space. And here's a picture of that Kola super deep borehole. It took them 24 years to get to drill down to that depth. And what did they find? Well, they found some interesting things. Now, I used to work with shock waves a lot, and that's very similar to seismic waves. At 3 to 6 kilometers down, they found a metamorphosis. They thought they were going to hit basalt, but they actually came into a metamorphic rock, which bounced the seismic waves back, so it looked like it was denser. They found rocks saturated with water. It seems that water is everywhere. They found species of microfossils. And a very interesting thing, they were predicting they would reach about 100 degrees C. They reached 180 degrees C. That was unexpected and hotter than they could have possibly expected the heat. And I'm kind of hypothesizing that it might be due to the heat of fusion if it exists. I want to give you a couple personal observations. First, scientists try, and I really believe this, they try very hard to form a consistent, well-structured picture of the universe. Unfortunately, most of the universe, as I was just talking about, is beyond our reach and always will be. The result, theories abound. Many theories, when they can't be definitely proved or rely on abstract models, have no way to be disproved. This is great for the scientist because there's no way of disproving his theory, but according to philosophers of science like Karl Popper, they fall in the realm of pseudoscience. This might be one of the major limits of science where first-hand investigation. We can't go up to see. We don't know from the standpoint of the red shift and how close things are because we can't go out there to measure them. We can't go down into the Earth. We're, in essence, living on a flat surface. And expansion tectonics has going for sound empirical studies. So with expansion, and this is one of the things that you'll find that I anticipate in the next 50 to 100 years, especially if they go back and they take out, James can tell you a little bit more about the geodesic data. James found an error. They found that the Earth was expanding, and they put in a fudge factor in all the calculations to show that it isn't. They're arbitrarily doing this. Now, before I leave, I'd like to do a very, very quick study, very short course on 19th century spectroscopy. A doctor by the name of Wollaston in England came up with he was trying to find the spectral lines of a number of colors in the solar spectrum, and he ended up by seeing these dark lines. That was back in 1802. In 1814, somebody that you might have heard of, Fraunhofer, Fraunhofer was a glass maker, and he rediscovered the dark lines. In fact, he actually mapped out 574 of them. And because he made optical glass and some of the finest glass in Europe, he went and used these lines to calibrate his glass so he could put different things in. By the way, he only died at the age of 39 because the glass makers used arsenic and a lot of other chemicals or elements back then, and they had very short lifespans. Then in 1925 and 1934, there was a man who, by the name of Talbot, who expressed the basic idea of possibly using these spectral lines to do chemical analysis. In 1842, Doppler came up and created the Doppler effect. And the Doppler effect later on, the reason I toss him in here, the Doppler effect later on was used to determine the rotation of the sun and actually the motion of stars away and toward us because of the shift with the velocity. Angstrom, who you've probably heard of, Swedish physicist, he actually went and found that if you discharge from metal electrodes in a gas, that you end up with two spectrums. So you end up with a spectrum from the metal, and you end up from a spectrum of the gas that is being used, which is significant because it had not been suspected that the gases could also give emission spectra. Then you end up with Swan. Swan was a man who demonstrated that Fraunhofer's D line in the spectrum of the sun was caused by the presence of sodium. One of the things that was very interesting here is that up to this time, everybody was wondering where the yellow line was in all the spectrums. They thought that this was maybe a common thing of all matter. Well, it turns out that the people that were actually doing the experiments weren't taking care for whatever element they had. They weren't wiping their fingerprints and the sodium on their hands off. And since the spectrograms are very sensitive, it was picking that up. And so everybody's samples were contaminated that way. Then you end up with a couple other people you've probably heard of. Bunsen. He investigated spectra of heated elements. He discovered a couple of elements along the way. Of course, he made the Bunsen burner. And Kirchhoff, you've probably run across Kirchhoff from the standpoint of electrical circuits. He was investigating the emission from black bodies, and he coined the term black body radiation, which all physicists should know. And then you end up with some more. This is the 1860s now we're up to. Clausius and Boltzmann and Maxwell. Now, these people were all interested in gases and energy and what have you, so they were trying to apply some of these things, and they were very involved with looking at spectrums. In the 1870s, you got Lockyer. He was carefully distinguished. He was actually the founder of the journal Nature, and he introduced the term of true atom. Once again, nobody knew what atoms and molecules were, but they were talking about it way back then. Huggins was a very interesting character. He was an amateur astronomer. He was such a good astronomer that the Royal Society of London, I guess, or England, went and gave him telescopes to work with. And his wife was really heavily into photography back then. This is when it was brand new. And they did a lot of work with photography and light from stars. He used the redshift of light to measure the velocity of stars moving toward us and away from it. Very interesting man. Then, of course, it was Lord Kelvin, physicist, engineer, did mathematical analysis of electricity and formulation of the first and second laws of thermodynamics. Of course, he went and correctly determined the value of absolute zero is approximately minus 273.15 degrees C. And he wrote a paper on vortex atoms, and I put some up here to show you because they had all kinds of crazy ideas. I mean, look at this one. All ways that atoms could be related. Nobody could figure out what these doggone spectral lines were. Hertz came in. He proved the existence of electromagnetic waves. Balmer actually was a mathematician, and he worked out a mathematical series for dark spectral lines called the Balmer series. And the interesting part about this I found is that he has M is kind of an index of how far you go. He predicted lines out there that Angstrom had observed, and Huggins, who I talked about, the astronomer, actually found these lines in the hydrogen of white dwarf stars. And then, of course, in 1897, the year my father was born, J.J. Thomson was credited with the discovery of the electron. And in 1913, Niels Bohr came up with a modern theory of the atom, the construction of the atom. And the orbits had to have certain quantum sizes so that to jump between them, use discrete changes of energy corresponding to the absorption and radiation of a photon. This was used to explain why electron orbits are stable and why elements absorb and emit electromagnetic radiation. In other words, the mystery of the black spectral lines had been solved. Now, the whole point of this little exercise is it took them 110 years to solve the mysterious experimental black spectral lines before the underlying physics behind the observation was understood. In the meanwhile, during that whole 110 years, those black spectral lines were used in many applications, as I've talked about, in chemistry, physics, and astronomy, greatly advancing our knowledge in all of those fields. Cold fusion today presents a similar challenge. We see the results. There's no theory behind it yet. Hopefully, it's not going to take another 110 years, although from the standpoint of the time that cold fusion was announced around 1991, 89 or 90, 91, that time period, it's been almost 25 years. So, we might be creeping up on this. I don't know. I would assume with our knowledge today that we'll be able to understand this. But this cold fusion is throwing physics completely into a loop because the fact that you could put two nuclei, positively charged nuclei, together and fuse them with no temperatures is really, to me, significant. The overall conclusions, we do not know what we do not know. And I think that this applies today as well as most other places. Some people go and they really, lots of things are invisible, but we don't know how many because we can't see them. And before I leave, this is a expansiontectonics.com. This is James's website. I have two items. One of them is his copy is in the proceedings, which is the paradigm, new mechanism for mass increase. That's basically what I've gone. In the proceedings, I've added a little thing about the pair production, which I had to cut when I did the article. And I also have a thesis that's available at James's website. If you go to the home, down to publications, and down to external links, is Rhetoric and Paradigm Change in Science. And I take 3 case studies there. I take Expanding Earth, Hubble, and Alphen with the plasma universe. But you can always get that there. And so that is my talk.
Hey, very good. Thank you so much. What we're going to do is take questions, and what I'm going to do is ask those people who would like to ask a question. We can do it 2 ways. Either you can ask the question, I can repeat it because we're only using a microphone here or if you want to come up yourself. So, anybody has a question? Okay.
I'll go ahead. I believe that Earth is increasing in size, expanding, because we picked up some material from the sun's explosion. However, if it is increasing the rate that is indicated here, I think the moon will have sucked into the Earth a long time ago.
Did you hear that?
No.
Okay. He said that he believes that lots and lots of material comes from the sun, but because of that, he would also believe that the moon would be sucked in as well if it's that much material coming from the sun. Is that correct?
Yeah.
Okay, that's his
Okay.
comment.
Well. Well, my comment to that is if my hypothesis is correct, the moon might not have as much water, and if it's a water phenomena, because water, I mean, is all over the Earth's surface. So I think that might be the reason why Mars isn't expanding. Also, it might be very unique to Earth with the compounds in the. I know James will say that the compounds or elements that you find on the Earth would be very similar to the elements that you would have on Earth, but I know water on the moon, so I don't know. I mean, that's one explanation which I can come up with, but definitely,
Okay.
you know,
All right.
James.
Okay, we got that. We got it.
Okay.
Okay. Another question?
No, that wasn't Cameron's question. Cameron was wondering why the moon is not growing. He's saying, if the earth expands, why doesn't it suck the moon?
No, that's what I said.
Yeah, he answered that, is it why isn't the moon growing?
Oh yeah, he said sucking the moon into the Earth's because it's got so much material coming from the sun.
Because it's growing in mass. The earth is getting heavier, why doesn't it suck the moon? Now, based on measurements, here that the moon is leaving the earth 4-7 million years a year.
Well, I can actually answer from reading people asking the same question because lots of people believe the moon is expanding its run.
It very well could be, but actually, take a look at that 3 billion years,
Right.
where it did not end up. I mean, that to me is as big a question. In 3 billion years, that's an awfully long time before you ended up getting any appreciable expansion.
Yeah, the question was, I get it now, is the moon's going away about a quarter inch a year, and he wants to know if the Earth's expanding, why isn't the moon coming in? Is it
I don't know. Is there any astrophysicists there? I don't know. I don't know. That's beyond my pay level.
Anybody, question, go ahead.
But I do know that explanation for it, it's because of the tides on the earth. The earth, because of the tides, it's accelerating the moon.
Oh, the Earth's on the tides is accelerating the moon, is what he said.
The earth's rotation is faster than the moon.
Okay.
I won't bet against it. I won't bet against you.
Another question? If nobody's giving a question, I do have a question, and it's just you're talking about cold fusion. What is the for us that don't study it as much? What is the problem there that physics can't explain in cold fusion that you're saying?
They can't explain how you get through the Coulomb barrier with no exotic byproducts. It's just goes against it. I heard a lecture from a man who was a professor at MIT talking about it, and he's an excellent theoretician and experimentalist. For 20 years, he's been studying it, and there's no explanation. It's just something that is not supposed to happen. The same way as you can't push two north poles of a magnet together. You're not supposed to be able to do it. There's all kinds of theories. I mean, I'm familiar with tunneling, and tunneling is where you can get through a barrier because of the quantum wave equation, but it's just something that nobody understands yet.
Okay. Okay. Any other questions? Oh, well, thank you so much. I think
James, I expect some feedback on my hypothesis from you.
Okay. What we're going to do now, I think, is we're going to go till 6 today. All right. And at 6 to 8 is when we're going to be going over to the point. That gives us a little bit. So I would suggest we take a break, get James ready for his talk. We're on Facebook Live. I don't know if we can keep this going because it doesn't matter. And so, oh, you need it, yeah. Well, maybe we can get you hooked up. I don't know. Maybe Franklin could hook you up. We'll see if we can hook you up on this through another computer, and you can throw tomatoes at James when he's talking.
Oh, that would be excellent. But he's my mentor. I mean, he is the person who first asked me, "What are my thoughts?" And now he's got so many of my thoughts that he's probably trying to have me shut up. Right? Right, James?
Okay, all right. We're gonna take a break right now, and then what we'll do is I'll talk with you. I'll get you off the speaker and stuff, and we'll talk. And let's see if we can get you on another computer. I'll talk with Franklin here. Okay?
That sounds good. Thanks for your participation, everybody.
Thank you. Yeah, we're going to keep the conference open, and we're going to have Franklin here join as a moderator and see if he can steal it from us, and then you'll be moving to his computer.
Oh, okay. Is this the same number and everything?
Yeah, no. Just stay where you are.
Okay. Well, I've got to go and eat.
Take a break.
Okay.
Okay, go ahead. You should be able to come back on, and you should be still here. So go do whatever you want. Okay.
Okay. Sounds good.
Okay, I'm going to mute you as well.
I hope this was okay. The presentation.
Go ahead. Go ahead.
I hope the presentation was okay for you.
Oh, it's great. In fact, we're recording it. I better stop recording it too.
Okay.
Here, let me stop.